We're now going to start our discussion of reactive programming. And this is a paradigm I've hinted at. We've taken a look at a few very simple examples of reactive programming, but now we're going to explore this paradigm in great detail, beginning with a discussion of reactive programming principles. And there are four key principles that underlie reactive programming, and that is responsiveness, resilience, elasticity, and being message-driven. And we'll also talk in this part of the lesson about the benefits of applying reactive programming. We'll also talk later about some of the challenges of applying reactive programming as well. So what is reactive programming? Reactive programming is an asynchronous programming paradigm. We'll talk more about what that means in a second, which involves processing streams of data, which should actually be familiar to you because we've talked a lot about Java streams, and propagating changes throughout a stream. And that's a little bit different from the way that Java streams works. And we'll talk more about that as we get into the nitty-gritty details of all this. What it does is it takes a bunch of operators and it composes them together using asynchronous and event-based sequencing. Ideally, the operators are non-blocking. And that'll be a big focus of how we're going to show examples of the reactive programming paradigm is by using non-blocking operations. You can do blocking operations with reactive programming, but it sort of misses the point. These operators can be mapped transparently to one or more threads. That's one of the other kind of cool things about this is you can change the context in which the operators run relatively seamlessly, and this gives you some additional flexibility you wouldn't have using Java streams. It's a bit more flexible. And one of the consequences of doing things like this, and this is actually one of the driving motivations behind reactive programming, is to be able to have a pool of threads where you don't have to start and stop them. So keep in mind when reactive programming first came out, which was probably maybe a decade or so ago, the main focus was on traditional environments with traditional Java threads where starting a thread was fairly expensive. And so you wanted to have a pool of threads, and then you wanted to be able to multiplex a bunch of non-blocking or asynchronous operations in the context of that pool of threads. Nowadays, with things like virtual threads, some of the motivation for this has disseminated, no longer is important. Dissipated is the right word I was looking for, as dissipated. However, it's still a useful model for other reasons, which we'll talk about. Reactive programming is particularly useful for certain kinds of scenarios. For example, processing user events. Things like mouse clicks or movements on a touch screen with touch events. Signals that are coming in from GPS location tracking hardware or other types of location tracking hardware, where you've got a stream of events coming in. Android and iPhone are both examples of platforms that have to deal with lots of events. So you might have Android. In fact, there's a version of reactive programming that's focused on Android called RxAndroid, and it allows you to take these events and process them in some interesting ways. You can also use reactive programming to respond to and process so-called latency-bound events, where you're trying to ensure that the operations run in a low latency or quick responsiveness context, even if you're dealing with input and output. So a good example would be handling asynchronous networking I/O in a publish-subscribe environment. So you might have something where you've got Twitter messages, or as they call it now, X messages, that are coming in to some type of sentiment analysis module, and you want to be able to filter the incoming Twitter streams, tweets, analyze it, and then group the results in various ways to graph and disseminate to people who want to see what's trending in the Twitterverse. That would be another example. We're going to be using reactive programming quite extensively to communicate between microservices in modern web-based computing environments. So if you take a look here, we have clients that talk to some kind of API gateway, and then that API gateway turns around and disseminates the incoming requests to a bunch of microservices that do various things, and all of that can run in a nice asynchronous way, which has many virtues, which we'll talk about. There are four key principles that underlie reactive programming. The first one is responsive, which means you want to be able to provide rapid and consistent response times by establishing upper bounds to prevent delays and deliver consistent quality of service and quality of experience. So you don't want to have things block. That's the basic idea. So you shouldn't, in a reactive program, you shouldn't see the dreaded hourglass of death, or the spinning wheel of death that you would see on platforms that have blocking operations for the user interface. You also want the system to be resilient. It should continue to be responsive and do processing tasks even if there are some failures, typically called partial failures. Obviously, if somebody cuts the network with a backhoe or a meteor strikes the data center, it may be difficult to respond right away. Some things, if you bring the entire system down, then you may have other problems. But if you have some things fail, you don't want the failure of some operations to bring everything to a screeching halt. So that's what we mean by resilient. Another key theme here, which is enabled by reactive programming, especially when coupled with other stuff, is the notion of elasticity. We want the system to remain responsive even if the workload varies. So as the workload goes up, what we would ideally like to have happen is we'd like the system to be able to auto-scale, either by using more cores on a single computer or being able to use more cores on multiple computers in some kind of cluster or cloud computing environment. And then the final principle, which is a little bit different from the other three, is this concept of message-driven. And this is really more about the implementation architecture, where you want the design of the system, its architecture, to be loosely coupled by passing messages asynchronously between different components or objects. You want to be able to isolate stuff so that some things can run in one place in a way that's transparent to where other things run. You don't want to have to hard code all that logic into your system to make it tightly coupled and difficult to evolve and maintain over time. This is a bit more of an implementation detail compared with the other three principles: responsiveness, resilience, and elasticity. We will see that this concept of being able to be message passing based and asynchronous and loose coupled and location transparent really becomes relevant when we start talking about web flux, which is taking reactive programming and injecting some steroids into it so that it can work effectively across computing boundaries. So we'll be talking about that. There's a whole slew of reactive programming frameworks, reactive streams frameworks, that implement these reactive programming principles. Some of the ones we're going to talk about will be Project Reactor. We're going to focus on Project Reactor. In other courses I talk about RxJava, and there's a bunch of other things in other languages like Akka, and there's stuff that's in Scala and so on. So there's a bunch of different ways. There's JavaScript implementations of this as well. So that's the end of the quick overview of reactive programming principles. Obviously, at this point, you just have a vague notion of what's going on unless you've learned about this stuff before. So we will continue to deepen the coverage as we go through this.